Good evening, everyone, and I welcome you all to today's live session. We are into the week 11 live session for the course Nonlinear Vibration, NOC25 me57. And till now, we have completed 10 live sessions in which we have discussed a lot about nonlinear systems, how to solve nonlinear system, what are the probable options of solving nonlinear systems, and about the numerical methods, analytical methods, parametric excitation, and various things like that. Then we have also talked about the characteristics of nonlinear system response. And this week we will be discussing about what has been taught in this week's lectures and the questions we'll solve so that it will be helpful for you to solve the assignment problem. Okay, so coming on to the overview of what has been taught this week. So this week was mostly about, there's some issue. Yeah, now my screen is visible. Okay, so this week was mostly about discussing that about what are flexible nonlinear systems. Firstly, it was more about what are flexible systems, what are the problem with the rigid systems, why do we need the flexible systems. Then the discussion was carried forward to the excited cantilever beams and how can we actually use these kind of a cantilever beam in order to harvest energy from it by using a piezoelectric energy harvesters. So I'll not be spending much time on the overview because everything has been discussed in an elaborative way in the lectures. So I'll directly jump onto the questions as of now. So coming on to the first question, which says that what are the disadvantages of rigid system? So this first requires the definition of what is a rigid system. What is a rigid system? So, we have been studying about engineering mechanics since, I guess, a very long time because engineering mechanics is usually introduced in our physics course only during the school, and then it is further elaborated when you study engineering. So, we talk about the equations that we study in physics. We talk about the velocity equation. We talk about the acceleration equation. We talk about the position and everything. Sorry. So, the question is that these are applicable for a rigid system. That's fine. But then what is a rigid system and why the equations are applicable only for the rigid system and not for any other kind of a system? So you see, when we talk about rigid systems, the mechanics got divided into three categories. One was for the fluids, which was known as fluid mechanics. Second one was on the basis of deformable solids, which came to be known as the mechanics of solids or mechanics of materials. And the third one was based on the rigid system, which came to be known as engineering mechanics. Okay, so when we talk about a rigid system, what do we mean is if I take a cube, Suppose there is friction present on the surface. This is a cube, and these are 2 points present on the cube, A and B. Okay. Now, as soon as I apply a force on this cube, what is going to happen? A friction is going to act where? In the opposite direction. Anyways, for now we'll assume that this F is definitely greater than the frictional force. In that case, what is going to happen? My cube is going to change its position like this. So for now, if I assume that the center was at X, now the center is at X plus delta X. Okay. And if I again now consider these 2 points A and B, if now I again consider these points A and B, what do I see? I see that after application of this force, my whole cube has been displaced by an amount delta x. Okay, the cube is displaced by the amount delta x. But if I look into the points A and B, okay, if I look into the points A and B, I see that these A and B points, they have not changed their position with respect to the cube, definitely. With respect to the cube, they have not changed the position. The A and B molecule, or if I say point or any particle, they are still wherever it was initially. So here only cube got displaced by delta x. Okay. So when a material exhibit this kind of a property, wherein the application of force does not change its shape, its size, or any kind of a deformation does not happen inside the material. Rather, the material's position changes, its velocity changes, that's fine. But its positions, the points that are inside the cube, that does not change. We call it what? We call it a rigid system. Okay, the internal points are not going to change the position, or we say that the cube is not going to show any kind of a deformation or any kind of a change in shape or size. Okay, so when we talk about rigid systems, what happens in them? You see, the deformation is very less. You cannot say that the deformation does not happen. Definitely there is some deformation uh, if we see the integrate properties, but we say that that deformation is very small as compared to the dimension of the cube, or maybe we can say a dimension, whatever the displacement it has encountered. Okay, that's fine. So, if I talk about what are the advantages of using a rigid system. Firstly, if we take some common example of a rigid system, what could be the common example of a rigid system? So for a rigid system, the most common example, if I would talk about for the rigid system, the most common example is going to be a crane, which we can see in the daily application. We can see a robotic arm, such kind of an example. Or if I talk about our day-to-day activities, mostly majority of things are made up of rigid materials. I would not say rigid materials, those are deformable materials, but we usually work upon deformation that is very small as compared to its dimension, and then we can conclude it that it is okay, a rigid system. Okay, so if I talk about the advantages, if I talk about the advantages of a rigid system, first and foremost is it operates mostly in linear zone. It operates mostly in the linear zone. Okay, so if it is operating in the linear zone, it is very easy to make a mathematical equation to predict its behavior under various conditions. Second, It is stable, which means it has less vibration. Third, what could be the probable more advantages that I can talk about? We have the linear zone, then we say that it is stable because it has less vibration as compared to the flexible material. What other? Since it has less vibration, it is more accurate, right? It is more accurate. And four, can lift more weight. It can lift more weight. These are fine. I guess these are enough. Now, okay, now I know it's, yeah, I know its advantages. But now if I talk about its disadvantages, its disadvantages. So if we try to think about the disadvantages of a rigid system, first is system has more weight. Because if I talk about a crane, which is used for lifting of any object, if you see the weight of that crane, the weight is very high. Now, if the weight is very high, then transportation is a problem. Transportation, transportation is an issue, right? Now, since the weight is more, right, we have more elements to be taken care of, and because of those more elements, we have to provide more power even for doing a very small work. So we have high power consumption. Okay, we have high power consumption. Then apart from that, if I talk about other things, what are the other things that can happen? Difficult to transportation issue we have already done. Yeah. Now see, since the weight is more, we can encounter catastrophic failure, and that is why we generally, when we operate a heavy object, we try to avoid any kind of a dynamic, very fast dynamical change, right? We prefer doing a slow process. So usually it is slow, and then we have one more disadvantage, which is the because of the mass, we have more inertia effect. Now, why is more inertia effect a problem? Because let us assume that I have a crane which has to lift a certain amount from a position and leave it to some other position. Now, lifting is not a problem. But if I am taking it to that position, it has gained some kinetic energy. Now, during this motion of taking the object from one place and keeping it in the other place, what do I have to do? I have to give the crane some kinetic energy in that span of time. I have to give it some kinetic energy so that it could move, and in that span of time only, it has to what? It has to also dissipate that kinetic energy so that when it reaches the particular position, it does not overshoot, right? Now, because our system has more weight, it is going to encounter more inertia, which needs to be dissipated, right? So that is also an issue. So now if I talk about the options that are given in the question, so the disadvantage of a rigid system are inaccurate position. No, that is not true, because for a rigid system, accuracy is easily attainable. We can actually attain an accurate position very easily because the vibration is very less and the system is rigid, and it is behaving, if it's behaving in a linear or even a small non-linearity zone, I know the closed form solution, I can know the closed form solution, and then I can control the system. So the first option is not correct. Second, complex. No, rigid systems are not that complex. Say their design could be complex, but if we talk about its behavior, it is not that of an issue. So if we say that it is complex, no, it is not complex. It is actually rather easier as compared to the flexible system. Then we talk about high power consumption. Yes, high power consumption is an issue. So this is going to be the correct option. And option number D, which is slow. Yes, the system does no, show slow response because definitely it has more inertia. So this is also going to be the correct option. So C and D are the correct options. Now we'll come on question number 2. Now we had talked about what are the disadvantages of a rigid system. So, what is a material that could be helpful for countering the disadvantages of a rigid system? Then the flexible systems comes. Okay. So, what is a flexible system first? So, a flexible system is a system which shows bending, rotation, and all these kind of a behavior, which means that its deformation, whenever a force is applied on it, its deformation is actually very high or equivalent compared to its dimensions. Okay. So for a flexible system, like if I take an example of a flexible system, a rubber band, or there are many examples of a flexible system. If we talk about just a rubber, small rubber material, it is also a flexible system. So there are various advantages of a flexible system. See, you see, the concept of introducing a flexible material came from the existence of the humankind, because you see that a robotic crane can lift a weight up to a certain amount or up to a certain proportion of its own weight, right? But a human, if the human trains his or her muscle properly, they can lift a weight equivalent to their body weight or even more than that. But you know, a human body is not a rigid body. But for a rigid body, saying that it could uh, take up more weight is not a very crude. Okay. So if we talk about flexible materials, that is possible because for humans it is possible, for biological membranes it is possible. Our muscles are able to lift up more weight. So then there was introduction of flexible materials that would behave somewhat like a human muscle or replicate like a human muscle, which could be advantageous to be used in certain kind of an application. Not everywhere. See, you cannot, at this particular moment, you cannot replace a crane with of a rigid material made up of flexible material. That is not possible at this point of time because it requires a lot of research and there is a lot of weight that is involved to be handled, right? For a flexible system, there are certain limitations as well. So first we'll talk about the advantages of a flexible system. Advantages. So advantages number one, lightweight. First one is lightweight. Then second we have, since the weight it is less, then definitely the inertia is going to be less, because if we are going to move or if there is any kind of a vibration in the system, it is going to have attained some kinetic energy, and then dissipating that particular kinetic energy is easier because the weight involved is less, right? So less inertia effect. Now, since the weight is less, the biggest problem that was there for a rigid system, which was the transportation problem, does not is not that a major problem in case of a flexible system. So here we have easy Transportation. Now you see, when I talk about flexible system, see for a rigid system, when I was moving a rigid system from one place to another place, that movement was the reason from which I was getting some effort on the basis of which I was getting whatever output I required. In case of a flexible system, that movement is not the sole reason for the effort that I want. Okay, the change of the shape of the material, the change in size of the material, they also contribute. Actually, majority of my flexible materials are actually basically used because of its deformation and change of shape, because that leads to the effort which is required for my system to work, right? So now, if I say that there is more of a deformation and more of a change of shape is involved, so you see it requires less energy. If I have a 10 kg of material and if I want to move it from one place to another and I require a crane, it is going to take up, more energy. But if I talk about a flexible material, right, it is going to require less energy. Not, I'm not saying that a flexible material can lift 10 kgs, definitely not. But if I'm using a crane to, maybe lift 500 grams or 1 kg, that particular crane which is being used to carry hundreds of kgs is now being used to lift up 1 kg. That is of, you know, waste of energy, right? Because the sole movement of crane is also taking a lot of energy, na? So in that case, what I can do is I can use a flexible system, because the flexible system is going to require less energy consumption. Its transportation is easy, and this amount of weight it can also carry. So this has low energy consumption, right? What else? Definitely, it is cheaper than your rigid materials. It is cheaper, and its maintenance is also less. So we can write it is also versatile. These are my advantages of a flexible system. Okay. But now if I talk about disadvantages. Okay, first we'll maybe answer the question. The advantages of the flexible system are lightweight. This is the correct option. Better transportability. Yes, because it's light in weight, it is easier for the flexible materials to transport. High inertia. No, it has low inertia. It has low inertia effect. Okay, and because of that only, because of the low inertia effect, it is going to have fast movement, and hence the last two options are incorrect. Only the first two options are correct. Now we have had talked about the advantages of a flexible system. What if now we talk about the disadvantages of a flexible system? You know, though it seems very nice that the flexible systems can be used instead of rigid materials, and it could give us good performance, and it will be cheaper for us, and everything. It seems very good while listening, but it has many disadvantages. The first thing is it has less stiffness. For example, if I take these two rod, like this is of a rigid material, this is a flexible material. Okay, now if I apply a force P, same force, what I'm going to see is that for my rigid material, if I look into the bending, it is very less. But if I look into the flexible material, changes very high. In fact, so I have made an exaggerated view. It should be much less than this also. Almost like this. So what do I see? For a flexible material, the deformation for the same applied load is very high. Now, since this is very high, it means what? That the stiffness that is present in the flexible material is very less. So if I try to plot the stiffness property, this is going to be for a rigid material and this is going to be for a flexible material, right? Rigid material has more slope, or eventually it should be somewhat like this, almost straight. Now, if you see that if some material is having such less stiffness, what does this mean? That even if a very slow speed of wind is blowing, the flexible material is going to show vibration. This less stiffness is actually a problem with the stability. So, one of the biggest disadvantages, less stiffness. Because of the less stiffness, what is going to happen? It is going to show more vibration. And that is why, because of this more vibration and less stiffness, it becomes very difficult for us to control the flexible system, right? And because of that, since it is difficult for it to control, it is inaccurate. You remember, it is inaccurate because a rigid system is accurate because it had a high stiffness. I was applying a very huge amount of force, then only it was deforming, or my main purpose was actually the transportation or movement of that particular rigid material. But in this case, I'm actually changing the shape and size of the material, and because of that, it requires a very small amount of force. So even if there is a very small variation in the amount of force, the result is going to be inaccurate. And the main thing which we are concerned about, nonlinear complex governing equation. You remember, for the rigid material, we said that since it operates in a linear zone, so the getting a mathematical model and then finding a closed form solution, it was very easy for us. Even if it has a small amount of nonlinearity, it was possible for us to get the exact solution because we had discussed about many analytical, approximate analytical method which are applicable for a less amount of nonlinearity. But in this case, definitely we have a strong nonlinearity that is taking place. Now, because of presence of that nonlinearity, even if I get the governing equation, I cannot get the closed form solution. I mean, it's difficult. I'm not saying it's impossible, but it's difficult, right? So if it's difficult, then what option do I have? Then the option that I have is what we have been learning since the last 10 weeks. We model the equation, we get the nonlinear equation, we then see in which zone it is operating. If it has high nonlinearity, we'll take the use of numerical methods and then we'll find the solution and then we can predict how the system is going to behave, right? So that we'll discuss in the next question actually, because that is what the question is about. The problem encountered for practical use of flexible system may be avoided by. The first one for us is going to be mathematical model. So how is a mathematical model concerned? In mathematical model, we derive the governing equation, which is essentially nonlinear. Now, then we try to find out the approximate analytical solution. If we know that the particular behavior is going to be periodic and it does not have that much non-linearity effect, so we can use the approximate analytical solution. However, if it is operating in a very high amplitude of vibration and the response is quasi-periodic or it is periodically doubled or anything of such kind, then we can switch to the numerical method, and then we can find the solution on the basis of the numerical method. And using that numerical method, what I can do is I can determine the parameters at which my system is going to show what kind of a vibration, and then when I'm using the system, I can use those parameters to get the required oscillation. Okay, so that is what we do in a mathematical model. I'll write it: derive model, then closed form solution, or numerical solution. From numerical solution, what we can do is parameter identification for the required response. Second, control. Now, if I am able to do the first thing, it's fine. If I am not able to do it, because closed form solution is fine, but it comes with a limitation that it is not applicable for every kind of a solution and for every amplitude I want, every frequency I want. Getting a numerical solution is fine, but if I want to get a broad range of parameters, then doing this numerical solution and then finding it, it becomes very difficult. So then what we can do is we can use a better way, which is the control. You know, control is fine, but there is again problem with control, that we cannot just apply the control technique like that only. Then there are various things that needs to be taken care of. Anyways, if we apply a control strategy, what we can do is we can control whatever the vibration is happening, and what we can do is we can get what vibration I want. Like, the control is further divided into two categories. First is the active, and second one is the passive. So when we talk about passive control, it is very simple that for the passive control, we cannot keep changing the parameters with whatever the response is. It is going to be fixed for whatever parameters we have chosen. It is going to be fixed. Now, for the passive control, we have further three categories. First one is viscoelasticity. Second one is tuned mass damper. And then we have a third option, which is a sandwich structure. So when we are talking about passive control, see, we know that if there is any kind of, like if I consider a spring mass system, and if I give some oscillation to the spring, sorry, mass, it is going to show what? Vibration, which is fine. Now, if I apply a force on it, forcing function on it, which is changing with respect to time, what am I going to see? I'm going to see that there is a element of the natural frequency, then there is an element of what? The forcing frequency and everything. But now if I introduce a dashpot in the system, what is going to happen? We'll see that the transient response is going to fade out with time, which will be helpful in actually balancing out the vibration which is present because of the natural frequency component of the system. And only the forcing response is going to remain, right? So that way, what did we do? The introduction of dashboard in the system was actually helpful to control the response of the system, right? Initially, there was transient present. Now, when I introduced the dashboard, the transient got out, and now I have a periodic oscillation, correct? So, similarly, when we talk about flexible material, it does not have a structural damping. It essentially shows viscoelastic behavior. When we say about viscoelastic behavior, what we mean is that it shows elasticity and then it shows some viscous behavior as well. Yeah, that is why it is flexible now. It is like a combination of a fluid and a solid. It possesses property of both in between. So, if we consider the viscoelastic property of the system, or if we try while manufacturing of the material, if we try to give it some kind of a more viscoelasticity, then what we can do is we can avoid the presence of chaos. We can avoid the transient vibrations, or we can reduce the time for which the transient vibration is going to happen, right? So that is how viscoelasticity could be helpful for controlling of the system response. Now this is again a passive response. Why passive? Because with the change of vibration, this is not going to change. Once I've made my material and it has a certain viscosity, that viscosity is not going to change with time. The viscosity property is going to remain the same. Okay. Second one is tune mass damper that we have already talked about a lot in the previous live session. For the tune mass damper, we introduced, what did we do? We had a spring mass system and we introduced another spring mass system with it, and the stiffness and the mass of the system was selected in such a way that for the first spring mass system, which was our main system, whatever, like for example, if it was given a frequency f sine omega t, vibration f sine omega t, and if I choose my second spring mass system and the mass and spring constant values are such that the natural frequency of that is now equal to omega, then we saw that my first primary system, despite having a forcing of f sine omega t, was not showing any kind of a vibration. Why? Because the tune mass damper was able to wipe out the vibration into itself from the primary system. So that way, tune mass dampers could also be used for controlling the vibrations. Yeah. And for that also, we have to first pre-decide that what kind of a vibration is actually happening in the system. And when once we pre-decide that what is going to be the value of stiffness and what is going to be the value of the mass, we cannot, it does not change with time. It is going to remain the same. Third one is the sandwich structure. Now, what do we do in a sandwich structure? Like, for example, if I make my flexible system in such a way, such that it has two elements, the outer covering, the inner material. The inner material is soft, and the outer covering is hard. Now what? Now, because of this sandwich structure, it possesses property of both soft and hard material. Right, and because of this property, what we can do is, like, depending upon the thickness of the soft material, thickness of the hard material, what kind of a hard material is being used, what kind of a soft material is going to be used, what kind of a stiffness property they both possess, what kind of a viscous property they both possess, depending upon that, we are going to get what we are going to get a properties which are in between of both, and that way what we can do is we can utilize both the property of the soft material and the hard material and get the required response. Now again, this is a passive kind of a control, because once we pre-decide the thickness, material stiffness, viscosity property, everything, it does not change with time, it remains the same. Okay, now second comes the active control. Okay, now when we talk about active control, what is happening? So for the case of active control, as the name suggests, we will have some power to basically control the property of the system, so that the control becomes more, it could actually counter more domain of the vibration it has to encounter. Okay, so for the active control, we have MR placed elastomer. MR is Magnetorheological. Now, when we talk about magnetorheological elastomer, what happens is that initially I was having a rubber material and I was using it for whatever system I want. Now, when we talk about magnetorheological material, now if I take that rubber, I melt it and I add some magnetic particles in it. I stir it and then I dry it. Now, my that rubber is now converted into MR based rubber, right? Because now, along with the property of the rubber itself, it also possesses the property of magnetism, right? Because those magnetic particle, and if I apply the magnetic field across that particle, what is going to happen? Sorry, across that material, those particles are going to align in direction of the magnetic field. Now, because of that alignment and direction of the magnetic field, what is going to happen? Its shape is going to can change, its size can change, its properties like shear modulus can change, viscoelastic property can change, right? So now what advantage do I have? That what I can do is once I apply my MR elastomer, I can change the magnetic field and the property of my material is itself going to change. Its property is going to change, its deformation is going to change, length, breadth, height, everything is going to change with the change of the magnetic field. And that is why we call it MR based elastomer and it is a kind of an active control. It is active control, right? Because instead of using a flexible material which is just made up of rubber, if I use a flexible material which has MR magnetological particles embedded in it, now with the change of magnetic field, I can change its properties. Now if I change its properties, the range of vibration that it can encounter or the range of movement the material can show me, it would change, right? So that is what it is. And the second one is going to be piezoelectric patches. Discussion about piezoelectric patches has already been done during the lectures that piezoelectric patches are essentially used in order to, get energy or harvest energy from wind, right? Where there was a discussion that if we take a cantilever beam and we fix it on a open environment where the wind is blowing, now what is going to happen? If I take like for example, if I take the scale, okay, and if I fix the lower point and I start this starts oscillating like this because of the presence of wind, what is going to happen? Right now, if I apply a piezoelectric patch over here, now piezoelectric material, it shows two kind of a behavior that I've discussed already. We had a piezoelectric effect and then we had a reverse piezoelectric effect. So what was happening for the piezoelectric effect? What was happening if we would give any kind of a deformation to the system, it would produce voltage. And for the reverse piezoelectric effect, what was happening if we apply the voltage, it would show the deformation. So you see over here, if there is a piezoelectric patch over here, now with the bending of this, the piezoelectric patch is going to change its shape and size. Now because of that change, what is going to happen? It is going to induce voltage across this. Now when that voltage is used to extract energy, right? Then it acts as a energy harvester, right? So now this piezoelectric patches has a very important usage, right? So for the piezoelectric patches, if we use it, it could be used in a very important work like energy harvesting. But again, it's a nonlinear system and dealing with a nonlinear system is difficult. But then again, for the piezoelectric patches, we have a voltage which we could use in order to control the uh, dimensions of the system. Okay, I hope this is clear. Now, if we talk about the question, the problem encountered for practical use of flexible system may be avoided by mathematical modeling. Yes, option A is correct. Passive control, yes, option B is correct. And active control, yes, option C is also correct. So all the first three options are absolutely correct. Now we'll talk about question number 4. So question number 4 is that the generalized Galerkin's method is used to. Okay, first question is, I have a, oh, okay, okay. I have a, this kind of a material. Okay, let us say that it's an elastomer. Fine. It has some thickness as well, like this. Now, because of any kind of external forcing or any other kind of, let us just take the cantilever beam only. That would be an easier option. So you see over here, there's a cantilever beam. Okay, and let us say it is made up of a flexible material. Now, if I'm applying a force over here, P, okay, it is going to bend like this. Okay, if I leave the force, it is going to return. If I keep the force, it is going to bend like this and be there at the equilibrium point. If P is changing with time, it will keep on oscillating. Now, what is happening in the system? You see, with time, its angle is changing. Now, because of bending, its shape is changing. And definitely, since its shape is changing, its size is also changing. Though the effect may be very less on the size, but it is changing. So, what all are changing? With time, shape, size, and orientation is changing. Okay, this is true. Fine. If it's changing, fine. The question is, let us take two points of importance. One is going to be this point. Let's take some other color. A, B. Okay. Now I want to know what are the position, velocity, acceleration of A and B with time. Okay. Now, one thing is that I derive the equation in terms of time and I then try to find out the positions and everything. But will it be true? Because its shape and size and orientation is also changing now with respect to time. So how can we not consider that also while deriving the equation? So when we talk about kinetic energy itself, the kinetic energy would depend upon what? The kinetic energy at point A is going to be different as compared to point B. For point A also, you see point A lies on the back side of the cantilever beam. If I talk about a point like A dash, which is just in front of the point A. The kinetic energy at A dash is also different with respect to the kinetic energy at point A. Why? Because there is change in shape, size, and orientation. Right. So when we derive the equation of motion, we are going to get that the equation of motion is not just temporal equations. Temporal equation means the equation of motion is derived in terms of only time. Time is the only changing variable. Okay, it is the only independent variable that is changing. But here, along with time, the space is also changing, right? The space is also changing, be it the point if it is on the front side or it is on the back side, at what distance from the base it is, that is also changing, right? So when we derive the equation of motion we are going to get in terms of a partial differential equation, because we are going to see that along with time the position is also changing. So we are going to get a spatio-temporal equation, which is going to be a partial differential equation. Now I know how to solve OD, right? We have taught you how to solve OD. But this is a partial differential equation. How will we solve a partial differential equation? So what do we do is, for a partial differential equation, instead of applying a technique to solve the partial differential equation, what do we do is we divide the space into certain number of pieces, and then for each piece we find the temporal equations. For each piece we find the time dependent equation, and then if we want to find for any position a dash, what is going to be the position, velocity and acceleration, we have to link it with the temporal equation as well as the discretized equation for every piece that I make. Okay, we create a mesh, right? So the way in which we convert a spatio-temporal equation or a partial differential equation into temporal equation, a number of temporal equations. Number would depend upon how many meshes I want to create of my system. That is known as the generalized Galerkin's method. Okay, so generalized method is used to convert spatio-temporal equation, which is the PDE, into series of temporal equation. The space is discretized. I hope this is clear. It's very simple. We have a partial differential equation which depends upon the space and time. So we divide the space into n number of parts, and then we get the time dependent equation for every part, and then we solve the time dependent equations. Okay. So instead of solving a partial differential equation, we'll be now solving some n or n plus 1 temporal equation, and those n and n plus 1 equations will be related to each other because of the mesh that we have created. Okay, now we'll come to question number 5. Vibration is which kind of external energy source? So the first question is that what is an energy source? So energy source is nothing but a source from where we can extract the energy. Energy source is something from where we can energy can be extracted. Now, depending upon the properties of the source, or what kind of a behavior the source is going to give us, the source was divided into two categories. Okay, source was divided into two categories: high level of energy source and low level of energy source. Okay. Now, why do we call it high level of energy source? Because it occurs in high capacity. Yeah, it occurs in high capacity and it also produces high capacity of energy. Okay. High capacity of energy is produced. So, high capacity or intensity of produced. If I talk about the high level of energy sources, which occurs in high capacity, we have solar energy, we have wave energy, we have wind energy. There has been a lot of research that has been going on extracting the full power from the solar energy, wave energy, wind energy, so that we can get good amount of energy from these sources and we would not rely much on our consumable energy resources, right? Anyways, these all occur in abundance and hence are a good source of energy and they are able to give a high capacity or intensity of energy and that is why it is known as a high level of energy source. Now when we talk about low level of energy source, as the name suggests, it is going to give me a low intensity or low capacity of the energy. Okay, the energy that is produced. So low capacity or intensity of energy produced, right? They are able to produce low capacity of energy. I would say very less as compared to if we talk about the high level of energy sources. Now, what are the sources? Vibration, noise, heat. By heat, what I mean is the excessive heat, which happens because of heating of a machine. The question is that this noise, vibration, and heat, how is it even an energy source? So you see, uh, for example, I have a machine. Now, because of its operation, it is producing some kind of a vibration. Now, that vibration, what is it? What is happening because of that vibration? The efficiency of the machine is reduced. Excess of energy is getting, wasted because of the vibration. Because vibration cannot be produced without consuming energy. It is consuming energy. All right. Now, if I want to, now I cannot do anything in order to avoid that vibration. So at least what I can do is I can use that vibration to produce some energy or for any kind of small work. Like, for example, there is a sensor which is present over there on the machine or which is near to the machine, and that sensor requires constant power, constant energy. But the energy is very less that it requires. So, what I can do is I would take my machine. I can maybe, like, as we have learned about the cantilever beam, I'll just apply a cantilever beam and then I'll apply a piezoelectric patch. And since the machine will vibrate, the cantilever beam is going to vibrate. At the free end, there's a piezoelectric patch. The piezoelectric patch is going to vibrate. It is going to produce voltage across it. The voltage can be extracted in terms of energy, and that energy could be further useful, to uh, give energy to the sensor for the working of the sensor. So you see what we have done. We have increased the efficiency of my machine because earlier my machine was actually wasting the vibration energy. But now my machine is now using that vibration energy to power a sensor which is used for its own purpose only. And now we do not require any kind of an external energy, electricity, to power that sensor. So what has happened? We have used a low level of energy source, which is a vibration, to operate a sensor, right? So this is how low level of energy sources come into existence, the concept of come into existence, so that we are able to use every possible energy that is getting wasted. Now, when we talk about heat, let us say that we have a machine, a lot of heat it is producing. So what are we going to do? We are going to apply cooling mechanism, right? Now, during that cooling mechanism, if for example I'm using a fluid for cooling it, right? Now that fluid is going to heat up because of the heat that is produced in the machine. The heat transfer is going to happen, right? The water is going to get take up the heat, and my machine is going to get decrease in temperature. So the fluid is going to take the heat. Now, what if I use a fluid that has a low boiling temperature, right? Because of that low boiling temperature, the amount of heat that is being given to the fluid from the machine that could be used to convert my fluid into steam or gas, right? Hot gas. It will get, converted into gas. But that gas could be used where? It could be used for maybe for using a small turbine, for operating a very small turbine. That turbine will produce energy, and that energy could be used. Second way possible is that we use water, right? And the water is going to get heated. That heated water is going to get supplied to the homes or to the factory itself, which could be used as a source for the hot water. It would reduce the bill of the geysers, right? That is how the excessive heat of a machine could be used as a low level of energy source. Though it is not going to give us a very high amount of energy, it is not going to reduce lakhs of the electricity bill for the factory, but it is going to contribute to a small amount. And for the energy, even a small amount is very important. We are actually increasing the efficiency of the system that way, right? So that is how we differentiate the high level of energy source and the low level of energy source. We just write could be used for energy to drive small components that require less energy. Heat could be used for heating of water and further be used as hot water. So these are the probable uh, uses. So vibration is which kind of energy source? So it is a low level energy source. It's not a high level energy source because the vibration is not that very high, and extracting energy from vibration, that is also not very easy. So coming on to question number 6. Which of the following is the type of piezoelectric energy harvester? Piezoelectric energy harvester, we have already discussed. We have already discussed about piezoelectric energy patches and how it could be used for extracting the energy. Now, further, the piezoelectric energy harvesters are further divided. Now, we'll briefly discuss this. So, this is further divided into 4 categories. First one is linear. So, when it operates in the linear zone. Then we have nonlinear, operates in nonlinear zone. or shows high deformation. This is the first category, linear and nonlinear. Second one is single mode and multi-mode, right? So when we talk about single mode or multi-mode, it would depend upon what kind of a frequency range it is operating on. Okay, so we have single mode and multi-mode. It would depend upon what kind of a frequency it is operating in. Like for example, it could happen that only one frequency component is there, and it is playing the major role while energy harvesting. And it could happen that can be multi-mode. Like for example, for the vibration only from which the energy is being harvested, there could be, certain frequency, only a single frequency at which the energy is harvested. And it could also happen that a number of frequencies are present in the vibration from which energy is harvested, because it is not always possible now that the energy that is present, it is always showing a periodic oscillation with only the same frequency. There could be a random response also, right? Okay, coming on to the third case, which is with or without internal resonance. With internal resonance, what do we mean with internal resonance? Well, it means that the internal resonance is actually present. Okay, so you know what happens in internal resonance? Like there are multiple resonances, frequency resonance that could take place. In case of a nonlinear system, we know that for the sorry, not piezoelectric, parametrically excited system, internal resonance can take place. And if there are various frequencies that are synchronized with each other, we give an effect for which we call it as internal resonance. For the internal resonance, we can write as multiple resonance frequency synchronize under certain condition, right? Under certain condition. Basically, here what we see is if there is the effect of frequency other than the resonance frequency. We can write it as well. Effect of frequency other than resonance frequency. So there could be one wherein we could have the internal resonance, and there could be another where we will not have the internal resonance, which is going to be without internal resonance. Then we have a fourth category as well, which is on the basis of excitation. See, there is a piezoelectric energy harvester. So definitely there is going to be some kind of an excitation. Because of that excitation only, now we are able to produce the energy, right? We are going to harvest the energy. So on the basis of excitation, it could have parametric, direct, random, simultaneous. So based on what kind of excitation is happening, we could have parametric excitation. In parametric excitation, what was happening? We had a parameter which was changing with time and it showed periodic change of nature. So for example, if there is a parameter, let us say B, and it is changing with time like B sine omega t, then we say that it is a parametric excitation, right? And like which in case of a piezoelectric energy harvester is going to happen because we'll see that the effect of the electromechanical coupling of the voltage and the deformation, it has actually connected through a nonlinear equation between the voltage and the deformation. And if the voltage, if it is changing with respect to time, then that change of voltage is actually introducing parametric excitation into the piezoelectric energy harvester. Then there could be direct excitation, wherein there is going to be a presence of a force F sine omega t, right? Which does not have does not which is not actually a parameter because it is not multiplied with deformation or the velocity or the acceleration. So it is direct excitation. Then we could have random excitation. By random excitation, we mean that direct excitation is in terms of force. Parametric excitation shows some kind of a repetitive of periodic behavior. Random excitation could be that even if a direct excitation is there, or even if a parametric excitation is there, it is not periodic in nature. It is random with respect to time, right? Then we can characterize it as the random excitation, and then we could have simultaneous excitation as well, right? These are the four cases that can happen. Okay, so these are the type of piezoelectric energy harvesters that could happen. Okay, so now if we come on to the options that are given, so we have which of the following are the types of piezoelectric energy harvesters. So first is linear and non-linear. Yes, this is the correct option because on the basis of what amount of deformation our harvester is showing, it could be characterized as a linear piezoelectric energy harvester or the non-linear piezoelectric energy harvester. Eventually, if the movement is very small with respect to the dimension of the system, we would say it's a linear case because deformation is small, so we can approximately write it in terms of the linear equations. However, if the deformation is very large, it is going to be non-linear case. Then we have single mode or multi-mode. Yes, because of the presence of the frequency that is in the energy harvester. If there is a single frequency, it is going to be a single mode energy harvester. If there is more frequencies, then it is going to be a multi-mode piezoelectric energy harvester. Third one is with or without resonance. Yes, with or without internal resonance. We know that there could be the internal resonance or there could not be the internal resonance. So C is also correct option. And talking about D, parametrically excited. Yes, parametrically excited is a type of uh, piezoelectric energy harvester. However, along with parametric excited, direct excited, random excited, and simultaneously excited are also the probable options. So all the four options are correct. Coming on to question number 7, we have to write the constitutive relation for the piezoelectric material. So we know what a piezoelectric material is now, right? A piezoelectric material is a material which shows both a piezoelectric and the reverse piezoelectric effect. So if there is some kind of a deformation in the piezoelectric material, that deformation is going to lead to the occurrence of voltage or the accumulation of charge because of that deformation, and that accumulation of charge can be further extracted in terms of energy and could be used for any kind of a, application that we want, right? So if we have to write the constitutive relation, first we need to write about the variables that are being involved, right? So we'll first write about the variables that we will consider. So the variables are going to be Firstly, E, which is electric field. Then we have S, which is strain. Then we have D, which is nothing but piezoelectric, piezoelectric strain constant. Then we have T, which is the stress. Silent, which is dielectric. Permittivity, and at the end we have small s, which is elastic compliance. So these are essentially the variables which will be involved in writing the constitutive relation. So constitutive relations are written in such a way that it is applicable for a three-dimensional object. And so if I write the relation, firstly, if I would like to relate, here there should be a capital D, which is the electric, not electric, dielectric displacement. So remember, there was a piezoelectric effect and there was a reverse piezoelectric effect. So for the piezoelectric effect, we have this equation, and for the reverse piezoelectric effect, we have, okay, I hope this is clear, because in the piezoelectric effect, my dielectric displacement depends on the stress and the strain. And in case of reverse piezoelectric effect, my strain depends on what? The electric field that is applied, right? Now, if I would write it in the constitutive way, wherein we consider I, J, K in order to consider all three dimensions, it's like S, I, J, and D, I is going to be D, I, K, L, T of K, L plus these are going to be my constitutive relations in terms of I, J, K, L. Okay, I hope this is clear. And anyways, this has also been discussed in the class as well. So we will not be going much into this. So if we get this equation, okay, we can further convert it for the case of a thin beam. For the thin beam, for a thin beam, we essentially have S and D is equals to S of E, D, D of T, which could be further written as S of 1, D of 3 is going to be equal to this one, right? This one is going to be my equation. Now, if you see over here, if anyone asks that which dielectric displacement is going to matter or which D is going to take place, it's going to be D31 because D31 is then multiplied with E3, which essentially reduces the effect, right? Here, if you see DE, right, for the reverse piezoelectric effect, right? So D is multiplied by E and then it is produces the reverse piezoelectric effect. So it could be further used for solving the assignment problems. Okay, I hope this is clear. Coming on to this question. For a base excited cantilever beam, del phi by del S is given as, okay. So firstly, what is a base excited cantilever beam? So we have a cantilever beam. Let us suppose we have a disc over here. Okay. Now, if this cantilever beam, it gets displaced, something like this. Something like this. Okay. What is going to happen? There is a change in position, angle, orientation, everything. So if this was the straight line and this angle is considered as theta, this position is taken as S and this whole displacement is taken as V. From this position, if there is a very small variation, what is going to happen? We are going to get, this should be 5. We are going to get a triangle. We are going to get a right angled triangle of this form. We have this as phi, this as ds, and this as dv. Now for this angle, if I want to write sine theta, which is perpendicular by hypotenuse, I already know the value of perpendicular and hypotenuse. It is dv and ds. So sine of phi is going to be d phi by ds. Let us say this is v dash. No, this should be phi. It should be v. Okay, dv by ds, and we are calling it as v dash. V dash is nothing but the differentiation of v with respect to s. Now, if I now differentiate it further, if I differentiate v dash again with respect to s, am I going to get? V double dash is equals to what? Cos phi del phi by del s. Correct? Cos phi is equal to del phi by del s. Okay. Now, if I want to write cos phi in terms of v dash, I can do it because what do I know? I know that sine square phi plus cos square phi is equals to 1. So in that way, cos phi can be written as under root of 1 minus sine square phi, right? So if I write it that way, v double dash is equals to under root of 1 minus v dash square del phi by del s. Del phi by del s, right? So in that way, what can I write del phi by del s as? I can bring under root 1 minus v dash square on this side. So del phi by del s is going to be what? V double dash divided by 1 minus v dash square under root. This is what I am going to get. Now, if I want to write it in this form, in the form the options are given, though this is the correct option, okay, this is the correct equation, but you see in the option it is not given. In the option, the v dash square is multiplied with v double dash. So what is happening? So we all know about binomial expansion. You know what happens in the binomial expansion? If we have an equation whose power we have to compute, through binomial expansion, we convert that into an infinite series, which will further be useful to simplify the equation. Because over here, v dash square is actually coming in the denominator and I want to bring it in the numerator, but I also want to consider the effect of the nonlinearity that is present. Okay, so what will I do? You can write it further as del phi by del s is going to be v double dash to 1 minus v dash square to the power minus 1 by 2. Correct? Now, if I have 1 plus x to the power a, or maybe 1 minus x to the power a, for its binomial expansion, I can write it as 1. I'll consider only up to the second term. Okay. 1 minus ax. This is binomial expansion. Okay. So when I apply the binomial expansion over here, what is going to happen? I'm going to get del phi del s. It's going to be v double dash 1 minus 1 by 2. Here other terms are neglected. Further terms are neglected in this case. So what am I going to get? I'm going to get del phi by del s is going to be v double dash into 1 plus v dash square by 2. So this is the equation that I got. Now if you look over here, we have v dash square as well, and this v dash square has introduced nonlinearity in the system, right? So this is, although we have considered an assumption, because of the binomial expansion we have considered only up to the uh, two terms. So definitely it's, I would not say that it's a properly nonlinear case, because the proper nonlinear case would be the previous equation, which is this equation. But in order to simplify a bit, like we used to do for finding the solution of a nonlinear system analytically, is to find the approximate analytical solution, right? Because for some cases, even getting the approximate analytical solution is also a win-win situation for us, right? Because completely relying on the numerical solution, knowing the fact that there are certain cases wherein we can find the approximate analytical solution, it could be beneficial for us. Similarly, we have found it in that way. So if we look into the question, for a base excited cantilever beam, del phi by del s is given as. So for here, option D is the correct, right? This is our correct option. I hope this is clear. This was a very easy question. No, wait, not D. A is correct actually here. Plus V double dash square. We have V dash square. Okay. So 8 is correct. Okay. Coming on to question number 9. Which of the following is correct regarding torus breakdown, root to chaos? So if you remember last time we talked about root to chaos. We talked about root to chaos. wherein we talked about the different routes that would lead to chaos. There was a kind of a behavior that while changing the parameter value, there was a way in which chaos was happening, like it was not occurring all of a sudden. There was a way it was happening, it was taking a path with the change of the parameter values. So we studied about, period doubling, route to chaos, wherein, if you remember what happened in case of period doubling route to chaos, what was happening with the change of parameter, the period of my behavior was periodic, definitely it was periodic, but with time, uh, with the change of parameter, my response was changing in such a way that it was periodic, but its time period was increasing twice. From t, it went to 2t, from 2t to 4t, 4t to 8t, likewise, right? So that was period doubling route to chaos. Then there was intermittent route to chaos, wherein what was happening, we had a periodic response, right? But when we looked into the periodic response for a long time, there were some patches of time, irregular patches, where chaos was present, small patches. So when we further increased the value of the parameter, what was happening? Further introduction, we saw that those patches, the irregularly occurring patches, their occurrence increases. Their occurrence increases. And also the time span for which it was coming, it also increases. Further increase of the parameter showed that with the increase of the patches, the time period for the patches and the occurrence, there was a time that most of the response was chaotic and there were small patches of periodic response that was present. Further increase of the parameter led to the whole chaos response. The periodic response was completely vanished from my time response, right? So that was the intermittent route to chaos. Then we talked about quasi-periodic route to chaos. Then we talked about the quasi-periodic route to chaos. So what was happening in this case? We had a periodic response. As soon as the parameter changed, we had a quasi-periodic response. Now, when we say that the response is quasi-periodic, for example, if my response constitutes two frequency elements, such that the frequencies, let us suppose the frequencies are omega 1 and omega 2, such that the frequencies are in incommensurable. Now, when we say that the frequencies are incommensurable, it means that the ratio of the two frequencies is irrational. It's an irrational number. Okay. So that means that the frequencies are incommensurable. And incommensurable, let us write in bracket the ratio of the frequency is irrational. The ratio of the frequencies is irrational. So if that is what is present, then we say that our response is quasi-periodic. Okay. So there was quasi-periodic route to chaos, wherein we had periodic response. Then we had quasi-periodic, and this led to chaos. And this is with variation of parameter. Okay, I hope this is clear. Now, this is fine that we have a periodic response and we have a quasi-periodic response and then we have chaos. Okay, so we can say that in this case, what is happening? For a periodic response, we have a finite number of points in the point intersection. For a quasi-periodic response, we had a closed loop, right? If we had a closed loop, then it means that the response is quasi-periodic. And for chaos, the point intersection is going to show the presence of strange attractor if we have a damping present in the system. If the damping is not present, so it would show a random placement of points in the phase plane. However, since mostly in the physical world, there is no system that does not have the effect of damping in it or the any kind of a dissipation in it. So we'll consider as of now that damping is present in the system. So how does the variation of strange attractor takes place? Strange attractor goes from finite number of points to closed loop to strange attractor. It should not be strange attractor. This should be point gray section. Sorry. Yeah. Finite number of points to closed loop to strange attractor showing change from periodic to quasi-periodic to chaos with change of parameter. Okay, this is fine because this is quasi-periodic route to chaos. But you see, the question talks about torus breakdown route to chaos. Now, if you remember that for quasi-periodic response, the phase plot used to show torus. But it is not true for all the cases. In some kind of a quasi-periodic response only, the torus is going to be visible. Other kinds of quasi-periodic response may not even have a torus. It can have some other kind of structure, right? So, for a specific case of a quasi-periodic response, we have torus. So if my periodic response is changing into torus or quasi-periodic response for the torus, and then that torus is now, uh, broken into chaos. The torus structure is now broken into some random movement in the phase plane. Then we say that a system is showing torus breakdown route to chaos. Okay, so what is essentially happening is that we have a periodic response. Then we have a quasi-periodic response, which essentially consists of torus in the a torus in the phase plane, and this further leads to chaos, which actually happens by breaking of the torus in the phase plane into random points, which is chaos. So, quasi-periodic route to chaos is where a quasi-periodic response goes into chaos. But the torus breakdown route to chaos is a specific case of a quasi-periodic response wherein there is presence of a torus in the phase plane for the quasi-periodic response. So this is what we call as the torus breakdown route to chaos. I hope this is clear. So now if we come to the question, which of the following is correct regarding torus breakdown route to chaos? The system goes from periodic to chaotic. Uh, that we cannot say, because the system goes from periodic to chaotic for beta doubling response as well, for quasi-periodic route to chaos as well, for intermittent route to chaos as well. Okay, so the system goes to chaotic through period doubling route. No, the system goes to chaos through the breakdown of torus. Yes, this is the correct option. And the system goes to chaotic through torus doubling route. No, torus doubling is not which is happening. What is happening is that the torus, which was present in the phase plane for the quasi-periodic response, now breakdowns into random, placement of points in the phase space, which leads to chaos definitely. So option C is going to be the correct option. Okay, I hope this is clear. Now coming on to question number 10. Okay. Okay, firstly, the question number 10 and question number 11 are basically based on numerical solution. So we'll be using MATLAB for it, and we'll do it in MATLAB, but first I'll just write the equation so that it will be easier. So when we talk about a Rosler system, it is essentially a three-dimensional system which has dx by dt given as minus y minus z, dy by dt given as x plus ay, and dz by dt, which is given as b plus z x minus c. So we have three parameters over here, which are a, b, and c. So if you look at this equation, it is easy for me to write this equation in the OD45 domain, because it is essentially three first order differential equations. We have three first order differential equations. So it is easier for us to write, right? So we'll just write it and solve it. Okay. So this was for the Rosler system. The last question is about the Lorentz system. So the Lorentz system is essentially written as, it is again a three-dimensional system. Dx by dt is sigma y minus x. Dy by dt is x rho minus z minus y. Dz by dt is xy minus beta z. And here also we have three parameters, which are sigma, rho, and beta. Again, this is a first order differential equation. We have three first order differential equations, so it is easy for us to write. Now, for example, if I give you a equation which has x double dot, the function f, and then I have y dot, which is a function of x comma y. And if I now tell you to, simulate the system, can you do it? See, it's easy, and we have already done this earlier many times. So if some equation is given in this form, what will you do? You will convert it into first order differential equation. So firstly, y dot is essentially a first order differential equation only, right? So I don't have to do anything with y dot. Y dot is the first order only. But x double dot is a second order differential equation. Okay, so I have to convert x dot into two first order differential equation. How will I do it? I'll assume z of 1 as x dot, z of 2 as x double dot, which is nothing but z1 dot. Then I have z3 as y dot, right? I'll have to put these three equations. So you see, since I have one first order differential equation and I have one second order differential equation, so the total number of first order differential equations that is required to solve this system dynamics is three. So I'll have three first order differential equations, and with three first order differential equations, I'll be able to solve and get the solution. I hope this is clear. So this was our Lorentz system, and this is the Rosler system. And now I will switch to my MATLAB in order to solve these equations. Okay. I hope that my screen is visible. First equation was about the Rosler system. Okay. So the question was that, okay, I'll just open the PPT over here also. Okay. So the parameter values are 0.2, 0.2, 5.7, and there are two options, that is the response periodic or is the response chaotic. Okay. So we'll see. So if I open the MATLAB, 0.2, 0.2, 5.7, just make it as 0. We'll run the code. This is three-dimensional plot of x, y, and z. This position, which is x, and this is x versus y. Okay, so if you look over here, the response is random. Okay, and I think it is chaos, but then again, I cannot say it like that. If you remember, we have always focused on that we cannot say by merely looking at the time response or phase plot that whether the response is chaotic or not. So what do? We do again the test of the sensitiveness to the initial condition. So what do? We change the initial condition. We change it by a very small amount, and then we check whether our response is same or is it changing with time. If it is changing with time, it means that it is showing strong sensitiveness towards the initial condition, and then we could conclude that it is chaotic. So here we will put as 1. We'll again simulate the system. Okay, I hope it is visible. You see the time response up till some initial value, let us say 100 units. The response was always almost the same. However, after that, we can see the divergence of the response, which shows that the response is chaotic. So coming back to the PPT. So for this set of parameter, option B is the correct answer. Option B is the correct answer. Now we look at the second set of parameter values 0.35, 2, and 4. 0.35, 2, and 4. Yeah, we'll run the code. See, now if you look over here, I can see that the response is periodic, essentially. And it is very clear also, from the phase plot and the three-dimensional plot also, that there is a certain kind of a path it is tracing, and there are two loops that are present, right? But then we'll just, for the sake of checking, we'll check for the another initial condition. Now you see, when you look over here, what is happening? The response is exactly the same. So it's a periodic response. It does not show sensitivity towards initial conditions, so definitely it's not chaos. And it is not showing any kind of a torus or any kind of you know overlapping responses in the phase plot, so it is not quasi-periodic as well. So option C is going to be the correct option. Coming on to question number 11, which is based on Lorentz system, right? Again, we have two set of parameters on which we have to look into. First, we'll open the code. Yeah, so we have sigma 10, rho 14, and beta 8 by 3. Beta 8 by 3, sigma 10, rho 14. Okay, so we'll simulate the system. Okay, you see this is a equilibrium point where it is converging. If you look into the 3D plot also, it is actually making a spiral, three-dimensional spiral, and it is going to converge at a point, right? It is converging at a single point in the space, right? So what options do we have for it? System has periodic behavior for sigma this. The system has chaotic behavior. Well, both the options are incorrect because we neither have a periodic motion, neither do we have a chaotic behavior. We have a equilibrium state, right? It is converging to an equilibrium state. There is some initial transient which is further converging into equilibrium state. So both the options are incorrect. And if we look into the second set, we just have to change the value of rho to 25. Okay, rho to 25. See, this is the time response. Well, again, we cannot say anything about the time response, but see this. See the three-dimensional plot. It is very interesting. You must have seen this figure in many of the textbooks and everything. See this. what is happening? It is making two, you know, somewhat like a butterfly, two wings of a butterfly. Yeah. So essentially, what we can predict from here is that in three-dimensional uh, plot, we have, two kind of wells, right? One is in X and Y, and other is in Y and Z. And you can see over here, right? Here we see this oscillation, and this is vertical. And when we look into this oscillation, this seems somewhat vertical, right? So there is this interchanging. Once it's oscillating in this loop, getting out to the other loop, oscillating in this loop, coming back to this loop, this kind of interchange is happening, right? The question is whether it is chaotic or not chaotic. So again, the best way we do it is that we check the sensitivity towards the initial condition. They give us very small variation to the initial condition. And if that change leads to greater variation when time proceeds, then we say that it is chaotic. So we'll just write 1 over here, and then we will simulate. See, first we look into the time response definitely. So in the time response, you can see that up till this point, we have almost same response. Everything is just going in the same direction. But as soon as this level crosses, you can see how the behavior changes. Here it is showing the lower well oscillation. Here it is showing the higher well oscillation. So, and if we look at the amount of, see, 1, 2, 3, 4, 5, 6, 10 to the power minus 6, we have changed the initial condition by this small amount, and you can see that the variation is very high. So definitely it is chaos. Also, I wanted to look into this 3D figure because it seems very interesting. You know, this three-dimensional plot, like we were talking about, a random placement of points in the phase plot when we are talking about chaos. But if you see over here, these are not random placement. There is some, there is some kind of continuity that you can see over there. That there are two wells, two attractors, and the system is oscillating between these two attractors, right? And it seems very interesting, isn't it? It seems very interesting, and you can find this diagram in many of the textbooks and everything. So if we now look into this, the system has periodic behavior for this, and the system is chaotic behavior. So definitely option D is the correct option. Okay, so this is it for today's live session. Yeah, okay. So I'll just stop presenting. Okay, so I hope whatever has been discussed in this week's live session, it is clear to everyone. And in case you have any doubt, please bring your doubts in the next week live session, because we'll be having the last live session next week. And apart from that, on Wednesday, 12 p.m., I have kept an extra session, which will be a 1 hour session, in which we'll do a revision about what we have learned in this whole course. It will be kind of a revision for everyone. And if in case you have any doubts, we can discuss in that 1 hour. We can even extend the meeting if you want. So, okay, we'll meet next week, Tuesday, 6 p.m. And till then, okay, good night. Thank you.